In this lesson, we're going to talk about sound, which is a natural progression from talking about waves, because we're just talking about one specific type of wave now. So sound is a longitudinal wave or a compression wave, and so you can kind of see it visualized here, where when something like a speaker makes a noise, what happens is it compresses air in some spots together and then draws it out in other spots. Because the speaker, what it does is it vibrates back and forth. So as the speaker is moving forward, it's compressing the air in front of it, and then that compression travels as a wave through the air. And then as the speaker moves back, it rarefies or decompresses the air. Oftentimes we model sound waves as transverse waves. So you can see, like, we'll match up a compression to a crest and a rarefaction to a trough, just because it's a little bit easier to see what's going on. Okay. So one thing we learned about waves is that the speed of a wave depends on the material that the wave is traveling through, and only the material that it's traveling through and the properties of that material. And sound is no different. So sound travels at different speeds through different substances. With things like gases, the temperature really changes the speed at which the sound can travel. So you can notice that when sound is traveling through air at 0 degrees C, it can go at 331 meters per second. If sound's traveling through air at 20 degrees Celsius, it goes at 343 meters per second. In general, when you're looking at different speeds of sound, like if you look at the liquids there, you can see that the sound, the speed of sound is quite a bit higher than gases. So that state of matter, since it's more dense, it's easier for waves to travel much more quickly, because there's much less distance that has to be traveled when one particle bumps into the next particle. And then you can see in solids, the speed of sound is even higher. Okay, so the speed of sound can depend on lots of different things. It can depend on the temperature, like I said, especially with gases. It can depend on the density of the material. It can depend on like the rigidity of the material, the tension of the, how much, if it's like traveling through like a wire or something, how much tension. So there's lots of different factors that can control it. Okay. So one thing, like when we're talking about the speed of sound, you might have heard of, obviously probably heard things like airplanes going faster than the speed of sound, and then you get this sonic boom. Well, what happens is that because the object is compressing the air, and those compression waves can't move away faster than the object is moving, you get a lot of air compressed ahead of the object. Okay, and so that huge compression going by then causes a big change in pressure between when the object is there and when it's not. And so that's where that boom comes in. It's just the huge amount of compression. In this image here of the airplane, you can see there's like a cone around the airplane, and this can happen as the air that was compressed is suddenly, like now, because it's getting behind the plane, now it finally has a chance to decompress, and waves can move out, and that decompression causes a lot of cooling of the air. So rapid decompression, rapid cooling oftentimes leads to cloud formation. Okay, so that's how clouds form too. It's just a much slower process. It's like warm, moist air rises and then it decompresses as it gets higher and cools down, and you get cloud formation. Well, here it's just a very rapid formation. You can see videos of this happening on YouTube too if you look up like sonic boom. So sound has some different qualities of it, and one of the qualities of sound is the pitch of the sound, which is directly related to the frequency. So as the frequency increases, the pitch of a sound will increase. And the pitch of a sound is very important in music. And so what makes a musical scale is actually mathematical relationships of the frequencies. So I have for you here the ratios that make up an entire scale, from the lowest note on the scale, like the do note, to the highest note, the high do. And every time you go up an octave, you double the frequency. And then all the other notes, all the other 12 on the scale are defined by certain ratios. Okay, so when you look at, and I'll just kind of highlight here the major ones. So like this here would be do, and then re, mi, fa, sol, la, ti, do. So those are the notes on the major scale. Okay, and you can see that there's also the minors. When we're looking at what notes sound good together, it also, like things that are harmonious together, are ones that have small whole number ratios. So if you look at like what notes on the scale sound good together, okay, well certainly the lowest note on the scale and the highest note on the scale with a 2-to-1 ratio, you can't get a lower ratio than that, although I suppose 1-to-1, the note with itself sounds great. But that is going to sound harmonious. Okay, the next probably most harmonious increment on there would be unison with the perfect fifth. Okay, with that 2-to-3 ratio. Okay, and then if you look at where else are you going to have some good harmony. Okay, when you're trying to play them all together, I think because of the way it works out, that you can have, it's the major third. Okay, so those four all make up what's traditionally a chord. So when somebody plays a chord, they're playing the unison note, the major third, the perfect fifth, and then the octave up makes up an entire chord, like on a piano or on a guitar or something. And then you can make different chords by substituting some of those in, and some chords, sound happier than others. If you look at like something that sounds a little bit sadder, swapping out the minor third for the major third, it still sounds somewhat harmonious, but a little bit discordant too. Okay, so all that, the way music is going to sound to us all has to do with mathematical ratios, believe it or not. Okay, so one of the activities you guys are going to be doing is you're going to be making your own musical instrument by manipulating what frequencies are coming off of things. And you can do that by manipulating, as we'll see, like what length of material is vibrating. Okay. Another effect that we want to know with sound is something called the Doppler effect. And this occurs with all waves, but it's more noticeable to us with sound. And the reason for the Doppler shift is that sound waves can only move at a set speed through the air. So if the source of a sound is moving relative to you, you're not going to hear its actual frequency, you're going to hear something else. So if we look at this diagram of the police car would have to be traveling very fast for it to be this exaggerated. Okay? But as the police car is moving, which is a very scary proposition since there is no driver in this car, okay? What's going to happen is this sound wave here, this leading sound wave, was created when the car was back here. And so you can see that this dot I drew is the center of this first wave out here, okay? And then the car moved a little bit before the next compression was made, and so the car was here. So now, or thereabouts, maybe it was a little bit further over, but that's when it made this compression. And so I think, like I said, I think it's over a little bit, so that moment it was in the center there. And then the car moved more before creating another wave. And so when the car was here, then it made this wave, which has traveled off from that, but it was at the center. So you can kind of see that the waves, as far as the waves concerned, they're just radiating out from the center of where they were created. But since each new wave starts from a new position, they get piled up. And once the waves leave through the air, it doesn't matter how fast the car's moving. They can only move a certain speed through the air, which is not moving. Okay, so that's where the waves get piled closer together in front, which leads to a higher frequency and a small wavelength. and they get drawn out behind, which leads to a low frequency and a long wavelength. Okay, so this is that whole, like when a car goes by, you hear the meow kind of thing, because it's high pitch as it moves closer to you and low pitch as it moves away. This would also happen if you were moving, like if you were on a bike moving towards a car that was idling. If you were fast enough on the bike, you would hear that same meow sound, because it just wouldn't be as dramatic unless you really could bike very quickly. Okay. The other thing about sound that we know of is its loudness. Okay, so we can have two sounds and we can tell that they might be the same pitch and everything else, but they have different loudnesses to them. Loudness, is related to the amplitude of a sound, but it's not actually the amplitude of the sound. Loudness we talk about on a logarithmic scale. So if you remember, if you talked about pH, or if you look at how the Richter scale works for earthquakes, those are logarithmic scales, because there's such a huge range of amplitudes of sounds in our human experience that you have to talk about really big numbers if you're talking about, if you don't use the decibel scale. Okay, so let's say if you hear a sound and this amplitude here represents 60 decibels, which would kind of be like a normal conversation, then if somebody was shouting and they were getting it up to 70 decibels, the wave would be 10 times bigger. Okay? And then if they were really shouting and if it was 80 decibels, it would actually be another 10 times bigger. So you can kind of think of the loudness of a sound is proportional to the log, if we've talked about logs in math, okay, that's of the amplitude. Okay, so because the loudness is proportional to the log of the amplitude, okay, then every time the amplitude goes up 10 times bigger, the loudness gets 10 times more. Okay, so basically again, so loudness, you add 10 decibels every time the amplitude multiplies by 10 times bigger. So or the intensity, if the sound is 10 times as intense. And so here's just some different scales looking at where do we sit in terms of loudnesses of things. So basically we try to keep our life somewhere in the 60 decibel. It's a nice comfortable volume. Okay, some of you may listen to your music a little bit louder. You look at a rock concert, is what that says is at 105. Okay, you really want to stay below 100 decibels if you're not wearing ear protection, because above that can start causing damage. How quickly the damage happens depends on the loudness then. So it gets to some point and you get instant hearing damage if you're not if you don't have some sort of protection on. Okay. So sound is produced when you have a vibrating source, and that causes the air next to it to vibrate. And we can get standing waves in things. Okay. So if you are, and then when you make a standing wave, because that sits on the material really nice, and you get all this nice constructive interference at the antinodes, then you can get a very loud sound. The thing is, we want the antinodes to be placed appropriately. So let's think of if you have a bottle that you're blowing over, or just because to make drawing simpler, a tube, and if you're blowing over a tube, you want the air to be moving a lot, okay, to be able to hear it. And so the end of this tube, for the sound that you're hearing the most of, is one where you're getting a lot of change at the end. And so that's going to end up being an antinode. Right? Down at the other end of the tube, if the other end of the tube is closed off, okay, then the air isn't going to be able to move very much. So you want a part of the standing wave that doesn't move much. So you want to have a node there. You always want to have deconstructive interference happening there so the air is not trying to move against the side of the tube that can't move. So if you look at what sort of wave can make that with an antinode at one end and a node at the other. So again, there's my node. Here's my antinode because we're vibrating back and forth between these two states. That would be where the length of this tube would equal to 1/4 the wavelength. But it turns out we can't. So when you blow into a bottle, what happens is you're sending, when you blow, it just creates white noise. There's all sorts of different frequencies going in. Only the frequencies that will create standing waves are the ones that are going to then add together and make constructive interference and make those antinodes where they need to be so you hear them. The other ones get reflected inside there and they get just canceled out and you just don't hear them anymore. Okay, so since the length of the sound that we're going to hear is going to equal 1/4 of the wavelength, we can control the wavelength of the sound we hear by controlling the length of the tube. Okay, and so that's a way of making a musical instrument. So it turns out for a closed tube, so like the example of blowing into a bottle, I already showed you the fundamental is the one I showed you. That's the lowest frequency that you're going to be able to hear out of that tube. But that's not the only standing wave that fits in that tube that has an antinode at the end. Okay, so you can also have all these other patterns where you have an antinode like 1/3 of the way down and an antinode at the end. So all these are called overtones, and when you blow into a bottle, you don't actually just get the fundamental. You get the fundamental plus, like I said, because you're sending a white noise in. Plus, you're going to be picking up the first overtones and the second overtones and the third overtones. And that's going to be what's going to give it its characteristic sound is how does the fundamental, the first overtone, the second, and the third, how do those all add together? For an open tube, the length is going to be some multiple of half of the wavelength, okay? Because you have an open on either side, so you're going to hear the sound the loudest when there's an antinode at either end and a node in the middle, or some other thing where you have antinodes at the end. So again, your fundamental frequency is going to happen when your wavelength is equal to half, your wavelength is double the length of the tube, but then you're also going to have overtones on top of that, which are going to give you a little bit different characteristic sounds for an open tube versus a closed tube, okay? Because of those waves superimpose on each other. And so every instrument, every sound you hear is going to sound a little bit different because of what sort of overtones come on top of that. Okay, so that's considered like the timbre. So how those frequencies add up and what's the overall shape of the wave you get out of it. Okay. And this activity of the putting together sound thing, I'm going to have you do instead of doing that as part of the notes. So you can see, like, when you add two waves together, what does it look like? What does it sound like? Okay? So that's all there is for these notes. Hope you enjoyed.